Today's webinar is titled Considerations When Architecting Your Next SoC, NoC. Our speakers today are Andy Nightingale, Vice President of Product Management at Arteris, and Piyush Singh, Principal Digital SoC Architect at Aion Silicon. This is a live webinar, so if you have questions, please use the chat box and we'll answer it during the Q&A or after the webinar via email. Okay, we're ready to get started. Over to you, Piyush.
Sure. Screen visible?
Yes.
Okay, yeah, thanks everyone for joining us. My name is Piyush and I'm joined today by my co-presenter Andy Nightingale from Arteris. Today we'll be discussing considerations when architecting your next SoC with a particular focus on the role of the network on chip. So before we dive in, let me give you a quick overview of what we'll be covering today. So we'll start by looking at some of the key trends shaping SoC requirements that need to support AI-driven applications. And then from there, we will take a step back and have a brief overview of the fundamentals of NoC technology in terms of the basic building blocks and what aspects of a NoC impact performance. We'll then walk through Arteris's FlexNoC 5 methodology, where we'll see the process of configuring an actual NoC using Arteris's FlexNoC approach, and Andy will lead us through this section. We'll then move on to NoC architecture exploration and how to approach it, the methodology to apply, and what benefits it brings to an overall SoC project. After that, we will talk a bit about integrating a NoC into a physically partitioned SoC. Starting with a single NoC, we will look at the approach for partitioning and cover some of the practical issues to be aware of in this process. We'll then share Aion's best practices for deploying a NoC effectively, things that we've learned doing real projects and things that can help you avoid rework and get to a clean implementation faster. Finally, we'll wrap up with a summary of the key takeaway points and then open up to your questions. So with that, let's get started. So what are some of the current trends Aion is seeing based on customer interest in AI SoCs? So first of all, we're seeing a diverse range of use case classes. Typically CNNs for inference type applications, but also transformer models are becoming more popular. So with transformers, we've got encode only, which are the your vision transformers, and then you've got decode transformers, which are similar to LLMs. But in addition to that, we're seeing the demand for classical vision applications as well. And also there is demand for single chip AI solutions ever since DeepSeek had their success with relatively small model compared to the GPT ones. So yeah, single chip is in demand by customers. In terms of IP, we're seeing a mix of RISC-V and ARM for control plane tasks, and for compute plane tasks, we see custom NPUs, DSPs, and workload accelerators. There is also a strong emphasis on software hardware co-design. So emphasis on compiler tool chains, runtimes like Onyx and TVM. TVM is Tensor Virtual Machine. It was AI compiler tool from the Apache Foundation. I'll share more on that later in coming slides. And also software which perform orchestration and map these models effectively onto the heterogeneous resources. So based on these interests, what hardware features do we want to prioritize? So we want flexible topology, which can serve both memory-centric and device-centric workloads, mix of specialized accelerators and memory IP. We also want a robust coherency model, and from this we have options whether it's hardware coherency or software coherency or something that's a hybrid of both. And then finally, we want integration of proven and standard compliant legacy IPs. All of the above have an impact on the architecture of the NoC. In terms of classes of SoCs that we are seeing for AI applications, so we've got two classes here. We've got a heterogeneous solution and the dedicated AI solution. Dedicated AI solution typically targets the data center cluster applications. In terms of compute units, it's mostly one type, AI-focused accelerators, and the power is quite high for some of these devices. The development cost is high, but it's more streamlined integration process. And in terms of use cases, obviously, that's targeting just inference and training applications. On the other side, heterogeneous solutions integrate different types of compute units, CPUs, GPUs, NPUs, and DSPs. And because of the breadth of IPs that need to be supported, there is requirement for legacy support. So you could have IPs which are on old protocol standards, which are perhaps conforming to some subset of those standards, but the interconnect still needs to support those. Performance per watt, so yeah, moderate power usage. Development cost is high because of complex integration, and use case is broad. So in terms of coherency model, we are seeing two types of coherency. You got the hardware-based coherency, which is processor-centric, and then software coherency, which is more compute-centric focused. Hardware coherency is your usual AMBA, AXI, CHI, more recently CXL, cache and MEM standards. The primary overhead is the coherence traffic, and the challenge to scale systems with hardware coherency is mainly the snooping logic, if you have a snooping architecture, or the size of your directory, if you've got a directory approach. Software coherency requires support from your processor ISA to support the cache maintenance operations. And the purest form of coherency that we have is software managed memory, whereby a system doesn't have caches, but instead has your off-chip memory, and then on-chip you've got several SRAM blocks. And the coordination and orchestration of the workload is managed by the compiler. So yeah, these are the various forms of coherency, and we're seeing software coherency, in particular software managed memory, to be the choice for AI accelerator based use cases. So over to you, Andy. What do Arteris see as some of the industry trends here?
Sure, yeah, Piyush. Across the industry, AI workloads are exposing a simple truth, I believe, one which we've known at Arteris and of course Aion for some time, that compute isn't actually the bottleneck, data movement is. So XPUs need a massive sustained bandwidth, real-time systems require predictable latency, and energy budgets are dominated by moving tensors rather than actually computing them. So that puts NoC at the center of architectural decisions. So whether it's hyperscale training silicon, automotive ADAS, or custom NPUs, scalable, physically aware NoC IP is now essential to reach performance targets, meet power constraints, and keep these increasingly heterogeneous SoCs operating efficiently. And as a second point, I think, yeah, there we go, yes. So really looking at design priorities in the AI era as well as the second point, really AI SoCs today prioritize three things: bandwidth, latency, and energy. So bandwidth keeps accelerators fully utilized, especially when DRAM becomes the choke point. Latency is critical for real-time inference. Automotive, robotics, and edge systems can't really tolerate jitter. And energy efficiency has become a fundamental architectural constraint, because transformer models, as you mentioned previously, spend most of their power shuttling data across the chip. So these priorities all converge on the NoC, making its topology, physical alignment, and automation key to meeting power performance and area requirements as we see it. Okay, back to yourself, Piyush.
Sure, thanks for that, Andy. Yeah, so at Aion Silicon, we've deployed a number of SoCs using FlexNoC technology from Arteris. And here are some recent examples. So to give you an idea of the complexity, I've stated the number of initiators and targets. So we got the multimedia SoC, which is in the tens of initiators and targets, and then similar for the automotive SoC. The automotive SoC was actually functionally safe up to ASIL-D, and the NoC supporting end-to-end ECC for that. We also have a multi-core compute SoC, which had 100 of initiators and targets, heterogeneous IP mix, multiple switchable power domains, and FlexNoC supporting all of these requirements. So yeah, just give you an idea of the breadth of different SoCs that we've deployed with FlexNoC technology. So now we'll have a brief overview of NoC technology in general, and understand the basic building blocks and what aspects of this affect performance of a system. So in terms of topologies, we can think of NoC as fundamentally being of two types. So you've got your centralized NoC, where you have the interconnect in the middle of the SoC. And then you've got a distributed NoC, whereby the interconnect structure can form at least one loop around some blocks. Now you will come across topologies such as tree, ring, and mesh, and so on. All of these topologies can be reduced to one of these two structures. You could have structures such as a mesh of trees or a tree of meshes as well, which can be derived from one of these two types. And why the topology matters is because it affects your PPA. So choosing the right topology early on in the architecture process ensures that you have the right design in place, and it must closely match with the SoC floor plan. So having an idea of your SoC floor plan early on in the architecture process is beneficial to choosing the correct topology. In terms of NoC hardware IP units, so we can think of them as broadly four classes. So we've got bridges, which interface to the IP blocks themselves on one side, and then NoC on the other side. These perform conversion from the IP's native protocol into the NoC's generic protocol. There is ECC support in bridges as well if you require functionally safe features. And then the data path is what does the transport from the bridges, initiator bridges to target bridges. And the data path comprises switches such as muxes, demuxes, serializers, FIFOs, adapters, and so on. On performance, you have rate limiters, bandwidth limiters, regulators, as well as for security, there is firewall support as well. And then finally, we got the domain adapter, which is performing transitions between different activity domains, and also things like clock power voltage, domain management. And in addition to that, there is support for pipeline stages, inserting pipeline stages to assist with timing closure. So those are broadly your four categories of NoC IP units. And how do all of these IP units come together to form a topology? So the top diagram is showing a high-level view of a network, starting from an initiator bridge, going to a target bridge. So the forward path from initiate to target is called the request network. And then you've got a similar symmetrical network called the response network, which is in the opposite direction, going from target back to initiator. So as a transaction traverses the path from initiator to target, it will go through stages of traffic merging, go through links, and then go through stages of traffic splitting. But this is not necessarily a one one combination. You could have a cascade of these, as shown in the middle diagram. And just expanding a bit more on what comprises a merge unit, you see it's got a MUX with a placeholder for pipeline stages. Similarly, links have a placeholder for pipeline stages, and then you've got your split units, which is DMUX. And that then goes to targets. Some special NoC hardware units that allow for performance tuning. So you got your link with adapters. So say you got your initiator running at a fast clock and your target running at a slow clock. Your requests will need to be buffered so that the target, because the target is running at a slow clock, they need to be buffered and stored somewhere while the target is able to drain that buffer and receive those requests. If you have the opposite, where your initiator is at a slow clock but target at a fast clock, then your response network requires buffering. So the link with adapters provides mechanism for implementing this buffering in the NoC. You also have reorder buffers. So say you have an initiator which is issuing ordered transactions to several targets. Having the reorder buffer in the initiator bridge allows the NoC to send all those transactions to the appropriate targets, and then when the responses are received, the reorder the reordering is done within the reorder buffer in the initiator bridge. So this is basically to support protocol compliance, whereby if you have an IP sending ordered transactions to several targets, in order not to have the transactions blocked waiting on previous responses to come back, the reorder buffer mechanism allows for sending those transactions in parallel, and then the responses are rearranged in the correct order before sent back to the IP. And then finally, we have QoS units, which are responsible for providing more predictable latency and bandwidth behavior. And this is achieved by arbiter units, which are in the merge blocks within the NoC. So each merge unit has arbiters, and these arbiters can be configured according to some scheme in order to shape the traffic in a certain way and achieve a QoS requirement. So now Andy will take us through a methodology of configuring a NoC using FlexNoC 5's approach. So Andy, over to you.
Thanks again, Piyush. Yeah, absolutely. So we see here that really FlexNoC 5 brings a physically aware design flow that ties the NoC topology directly into the system on chip floor plan. So instead of building the interconnect and hoping it fits, we actually align sockets, paths, and pipelines with real physical distances. So that means fewer back-end iterations, more predictable time enclosure, and a topology that naturally helps designers avoid congestion, as we'll see in a few moments. So this methodology, in summary, improves performance, area, and power while actually reducing designer effort. So here's a real design scenario. So multiple DMAs accessing distributed SRAMs for scratch pads. A simple crossbar looks an attractive choice at first from the designer's point of view, but quickly this will run into scalability limits, too many wires, too much congestion. So FlexNoC turns that into an optimized topology with switches, pipelines, and partitioning that scales cleanly. So this highlights why a NoC-based approach outperforms ad hoc interconnect structures in modern SoCs. And we start by capturing network interface unit specifications, connectivity, and address maps, and importing floor plans. So this is left, def, or block images directly early in the process, and the tool generates a first pass topology tied to real layout constraints. Later stages refine it with tighter physical data. So the outcome is a consistent handoff from architecture to physical design, with the NoC always aligned to how the chip is actually going to be built. So FlexNoC generates an initial topology that respects the floor plan. This then allows a reset to rebuild a more optimal structure. So here's step by step, we collapse unnecessary paths, restructure switches, and reduce central congestion. So this iterative process transforms a naive wire-heavy network into a lean, physically efficient topology, really tuned for bandwidth and timing. And as congestion hotspots appear, we refine the topology using targeted filters, adding switches, redistributing traffic, and shortening critical links. So this turns large monolithic switches into a distributed fabric that's much easier to route and far more timing friendly. And the result is lower wire length, lower latency, and a smoother physical design. And this comparison shows the payoff. The initial big switch topology on the left is dense and congested, while the optimized version on the right has fewer wires, shorter paths, and significantly better routing efficiency. So it's a practical demonstration here of how physically aware generation directly improves PPA and the integration effort. And here we insert link groups and pipeline placeholders based on real physical distances down to design scale and propagation timing. So this makes timing closure deliberate rather than reactive. And by aligning placement, pipelining, and wire length constraints, FlexNoC here builds a topology that naturally meets frequency targets, even in large AI SoCs that we've been talking about earlier. And here we see why physical aware refinement is so important for modern AI SoCs. As we optimize the topology, we're not just rearranging switches, we're directly cutting this wire length. In the early past, the fabric stretched to around 40 meters of cumulative wire. After restructuring switches and aligning routes to the floor plan, that shrinks to roughly 20 meters. So having the wire budget means fewer pipeline stages, a better timing margin, a lower dynamic power, a much cleaner physical design. And this is the point where FlexNoC's physically guided workflow delivers real PPA gains. And this year, Arteris also launched its FlexGen product, which builds on FlexNoC and automates the entire topology generation process and delivers even more significant PPA wins. So this includes 10x productivity for the designer, 26% reduction in wire length, 28% shorter, longest wires, and better latency and area. And for AI and automotive designs, where complexity generally tends to explode, FlexGen turns what used to be a manual, expert-driven process into something that's really quite predictable, faster, and more scalable in far less time.
Thanks for that, Andy. So now I'll cover briefly how Arteris technical solutions are linked to Aion's methodologies. Yeah, in terms of wire and area reduction, we've got the packetization and serialization feature, which have been implemented into the NoC design process. And also on low power, we've got power disconnect feature and multi-level clock gating, which we've implemented as part of the platform management unit and power clock reset strategy. On legacy support, the requirement to support various legacy protocols and subsets of protocols. The requirement for that means, yeah, we need to support that for customers who have those kinds of IPs. On FUSA, yeah, functional safety requirement, that's part of Aion's FUSA strategy. On performance analysis, some CTLM models provided by the FlexNoC platform is integral to the Aion's performance exploration environment, and I'll cover a bit more about that in coming slides. The physical design process, that's integrated with the backend approach, and also on verification, we have automatic open test bench generation and test case generation provided by the FlexNoC tool. And that's important because the test benches provided by Arteris can be extended with specific Aion test cases, and that helps with the NoC verification process. Was there anything you wanted to add further, Andy, on this?
No, I think you've covered it excellently, really. I mean, the key point here is that our technologies, really complement each other's approaches, to building and integrating complex SoCs. So, really great summary.
Sure. So now I'll cover the approach for NoC architecture exploration, the methodology, and what advantages it brings to an overall SoC project. Understanding a bit more about the computational characteristics of current AI applications, we can think of them as broadly three categories, as I mentioned some slides ago. So we've got CNNs, which are typically the easiest and most efficient model class to implement on ASICs. We've got VITs and LLMs. So these have come about because of the transformer architecture. So with the transformer architecture, you've got a decode and encode loop. So a transformer with just the encode is your VIT, that's Vision Transformer. Similar to CNNs, but they have slightly different memory access pattern due to the attention mechanism implemented within the transformer structure. And then lastly, you've got your transformer with decode loop, which is an autoregressive model, which means every output that the structure generates is fed back into its input to generate the next output. And it keeps running this in a loop until all the outputs are generated. And because of this autoregressive structure, it becomes more challenging, relatively more challenging than VITs and CNNs to implement efficiently on hardware. So in order to study the behavior of these algorithms and how they impact the performance of a potential SoC architecture, we can think of an example such as the one shown. So we've got multi-core NPUs connected to a single on-chip interconnect, and that is then connected to several off-chip memory modules. And if we look at the data flows that typically occur in such a device, we've got the diagram at the bottom. So you've got the preload coming from off-chip memory, and that's going to your local memories, to a preload space. So the local memories are split into two sections. You've got the preload space and execution space. Both the preload and execution space need to be sized accordingly. So they could be equal, or one could be bigger than the other. And the core has access to the preload data as well as execution space data. And in addition to these accesses, which are local to a core, you've got inter-core accesses whereby a core can query the execution space of another core, and that becomes a remote access. So given all of these different types of accesses, and bearing in mind you could have tens or even hundreds of such cores in a system, how do you decide, number one, the partitioning of the local memories for all your cores, and then secondly, the optimal NoC topology, which can support the performance of a system like this. So in order to do this, giving a high-level overview of the process, we begin with the computation graph of the application, the AI application, which is described in terms of the various operators, which are the nodes, and then you've got the edges, which is describing the data flow between the operators. Such a graph is then analyzed by an AI compiler, which performs several transformations and analysis to work out what is the best partitioning of your execution and preload space, what is the trade-off in terms of sizes between the two, and what is the best ordering of your preload transfers, your remote accesses, your local accesses, and also the execution activity of each core. So what you end up getting as an output from the compiler is a bunch of potential schedules, which are mappings of the use case onto the device itself. And you have different schedules which the compiler generates. And then finally, you want to understand which of these schedules is the best one to choose from, and how do these schedules have an impact on your NoC topology. So you want to tweak your NoC topology, your memory controller configurations, clock frequencies, data widths, and so on, QoS settings, in order to satisfy the KPIs for the candidate schedule. And in terms of KPIs, you have different measurements, seconds, so time to first token, time per inference pass, inferences per second, local memory footprint in terms of your preload space, execution space, and then of course your system bandwidth and latency. So hopefully at the end of this performance exploration process, you end up with, which could be time consuming because there are lots of simulations and experiments to run. But by the end of this, you end up with the optimal NoC topology and configurations for your memory controllers. Part of the performance exploration simulations is the system C model of the interconnect, which is generated by the Arteris FlexArtist tool. Now FlexArtist is the UI which the designer interacts with to configure the NoC. So out comes the system C model, and that is combined with a model of your memory controllers, of which there could be many. And of course, you've got your hardware transactors. And that is your architecture exploration platform. And we typically build this in Synopsys Platform Architect. So Platform Architect is a well-known architecture modeling EDA tool from Synopsys. So that's your structure of how the exploration platform is constructed. And then you've got the workload model, which is the output of the TVM compiler. So these are your candidate schedules, which are imported into Platform Architect. And then you run your simulations. From your simulations, you have your KPIs, performance KPIs. You perform analysis on these KPIs and feedback any adjustments, if necessary, to your SoC architecture specification. If some use cases cannot be met, then the feedback goes back to the original product use cases to say some use cases simply can't be supported for such a platform. So it's a two-way mechanism there. Product use cases are informed by analyses from simulations, but then also the use case requirements need to be met by the analysis. In this platform, we can also swap the system C models with RTL. So you've got the swap, the arrow showing the swap. You could, as and when you have RTL available, you swap your system C model with cycle accurate models and observe how that changes your performance data, your simulation data. Also, you can swap the workload model with traces, IP traffic traces, if you have that available. So that's also another approach. And yeah, it's a three-step approach. So first, you want to do point-to-point simulations at max possible use case bandwidth for each initiator. So this ensures you've sized all your interconnect resources correctly. And then you move to step two, whereby you're running concurrent traffic simulations of the most demanding use case. So you want the worst case use case envelope. You want to ensure that your platform can support the requirements, the bandwidth and latency requirements for that. In this stage, you might need to modify your NoC topology slightly, but bulk of the work should have been already done in step one. Step two is a fine tuning. And then step three is co-simulation with RTL, where you have real RTL of the NoC and memory controllers to confirm that you meet performance. So that's your performance verification process. Step one and two are performance modeling. Step three is performance verification. Now I'm going to cover the integration of a NoC within a physically partitioned SoC. So why partition a SoC? Usually the requirement to partition a SoC is driven by backend requirements. They might find the need to harden certain parts of the SoC early if they are not expected to change over the course of a project. So they'd prefer to harden those sections first. But also it helps with the runtime. So if you're going to have lots of turnaround, lots of churn, then having smaller blocks, smaller sub blocks to take through the backend flow means you have a faster turnaround time. So with these partitioning requirements coming from the backend team, there is a need to partition your NoC accordingly. So we've got the partitioning flow, which performs the NoC partitioning. So starting with a single NoC as designed, the flow restructures the NoC RTL, as well as the design constraints and UPF descriptions of that. It has to be aware of the connectivity in between partitions. So the flow needs to manage the connections and make sure that the right connections are retained. And in order to prove that the partitioned NoC structures are equivalent to the initial NoC, we need to run formal equivalence, some kind of formal equivalence checking, such as formality, to compare the before and after. And then finally, you need to make sure that your top level power clock reset infrastructure is mapped accordingly to the partitions. So this diagram is showing an example NoC, an example integration of a partitioned NoC. So starting with the sections which are colored orange, you've got your FlexNoC, which are embedded in wrappers, right? So in between each orange block, I've shown arrows to indicate there is connectivity in between the partitions, but each of the partitions need to be embedded in a wrapper, and that wrapper performs your SoC level clock power reset management functions. There is also interconnectivity between the wrapper levels. So yeah, that's all in your always on power domain. So each of the gray blocks are your power domains. You've got your always on power domain, and then you've got two switchable power domains, north and south, which contain your IP blocks. And the power switching reset management of that is performed by your platform management unit. Previously, this would be the power management unit, but at Aion, we've seen the need to extend your classic power management unit with additional functions, SoC level infrastructure functions, and that's now been renamed to platform management to better fit the functions that this block performs. And then you've got your master reset generator, which does your power on reset of the main NoC domain, but that also propagates the resets to the sub partitions as well. So yeah, this is to give you an idea of what the high-level integration connectivity looks like for a partition NoC. On power management, so transitioning from power state on to power state off, a bunch of functions need to be performed, and the ones that are most relevant to the NoC are for power down are step 2 and step 4, right? So for step 2, you have the power domain switch to idle state. And what does that do? So first thing it does is it will disconnect the IP interface from the initiator bridge so that no transactions are received from the IP. Normally, the IP should have stopped generating any transactions, but in case it hasn't, it's safest to disconnect the IP first. And then secondly, step 2 is a process whereby you want to drain the NoC of any current pending transactions. So drain the NoC and then fence the NoC from receiving any transactions. And that ensures your NoC domain is clean and can be taken into reset, which is step 4. On the other direction, going from power domain off to on, you're doing the opposite with the power up sequence. So similarly, the NoC reset is deasserted first, and then the IP interfaces are reconnected, and then the rest of the power up sequence carries on until step 10, where IPs can then start generating new transactions. So in terms of best practices using FlexNoC technology from Arteris, we see 5 steps here. So first of all, get the specification right. Collect as much information as possible from all your IPs regarding protocol requirements. Get all your clock domain information, power clock reset information, activity domains, connectivity map, and address map as well. So that get your specification right first. And then step 5, start your RTL integration early. So RTL integration includes RTL verification. You want to start this early because that ensures your integration team have a NoC to start integrating and make sure that all their flows are pipe cleaned. As the project matures, you might have different deliverables to different teams. So for example, you might have a different NoC to deliver to your FPGA team compared to your ASIC team. In addition to these, you also have deliverables to verification team, as well as architects who want the system view of the NoC, system C view of the NoC. So all of these need to be managed. You want to perform your performance verification early, so that helps inform your topology choice and helps you work out what's the best topology to create in line with your floor plan. As the partitioning information comes, you want to integrate that. So have your NoC divided into separate partitions if required, and add pipes to get a clean boundary between the partitions. And then lastly, you want to add pipes for timing closure. So you add pipes to bridges to meet timing on your NIUs, and then you add pipes to the transport network. Step 11 is done automatically within the FlexArtist tool, so that's easier to do. You don't need any feedback from your backend team to add timing to add pipeline stages to your network, to your transport network, but you might need feedback from your backend team to add pipelines to your bridges. So to summarize, Aion can deliver SoC projects with faster time to market, and because of the capabilities of FlexNoC, we have less turnaround with a backend team, and that's helped significantly shorten project schedules, better PPA owing to the capabilities of the FlexNoC technology and the optimizations that it offers, scalable and flexible architectures. So the modular and tiling architecture has enabled scaling to large SoCs by isolating certain parts of a SoC as a sub-NoC, and replicating that several times has helped saved time and improve scalability. And then finally, performance optimizations with flexible topologies, wide data path options, reorder buffer options. That's really helped converge on the right performance, on the right NoC to deliver the desired performance. And integrations with other System C platforms like Platform Architect has helped in this regard. So with that, yeah, I'd like to conclude the talk and take some questions.
Thank you very much. Great presentation. Just as a reminder, there are 2 handouts in the handout section that you can download. So you might want to click on the handout menu. And now we'll do the Q&A. We do have some questions, but if you have questions, please type them into the question box and we'll get to those as soon as we can. First question, and this goes to both of you gentlemen. AI workloads are evolving fast and data movement is becoming a bottleneck. How does Arteris and Aion Silicon solve this problem?
Yeah, Daniel. Traditional SoCs and hence NoCs were designed around predictable, bursty, if you like, processor traffic. And as we've seen, really, modern AI workloads just aren't like that. They're memory bound, they're irregular, driven by compiler managed data movement across many cores. And that creates pressure on bandwidth, locality, and coherence models. So we address this with physically aware topology flexible fabric, if you like, that shapes the NoC design around real layouts and real traffic. And Aion, I'll let Piyush comment in a second, really complements this with workload-driven architecture modeling, validating communication patterns, long before we get to silicon.
Yeah, that's right. So performance modeling plays an important role in this process, because what we want is ensure that the architecture that we're going to build in fact supports the requirements of your SoC. So that means ensuring that we can model all the traffic patterns correctly and check and test whether the SoC model can support those kinds of traffic patterns. So the performance modeling aspect, and in particular the System C architect's view of FlexNoC, is key to understanding and demonstrating that the requirements can be met in terms of performance.
Okay. We have another question. Does FlexNoC integrate power estimation tools to explore different design choices?
I guess, Andy, you'll take that first.
Yeah, sure. I was just waiting for a taker. Yeah. Basically, FlexNoC exports all of the scripting needed to import the design into power estimation tools. So the quick answer is that it uses the best, industry EDA tools available to help make those choices.
Yeah, on power estimation, I know FlexNoC does output some information, and I need to check this with our designer. There is some estimates which FlexNoC provides, but yeah, in our flows, we have other approaches for estimating power, which are performed by the backend team, but I can get back to you on more details on that.
Okay, another question. Does Arteris N-Core coherent NoC have similar PPA advantages and tools and flows as FlexNoC?
Yeah, absolutely. Obviously coming from the same stable at Arteris, but tackling a different challenge in that of managing hardware coherency, as we saw Piyush talk about as an option previously. So there's a similar flow. There's a front-end user interface that enables you to configure up the topology, and then the exports from the tool. Yeah, as Piyush mentioned, similar to FlexNoC, there'll be some estimation, some rough guidance inside the tool, but really the exports into industry standard estimation tools are where we're at here with N-Core coherent NoC.
Another question, can we integrate traffic models so that we can have traffic traces?
Yes, yeah, that is supported. Yeah, you have support for running traffic traces within the modeling platform provided by FlexNoC. So FlexNoC provides their own modeling platform for analyzing performance of the transport network. But in addition to that, you've got your platform architect model, which is modeling the full SoC platform. In either of these platforms, you can run traffic traces. Of course, running it in platform architect allows you to analyze the performance of the full SoC as opposed to just the NoC transport network. So yeah, that's possible, but you can use traffic traces as well as the computation graph approach.
Okay. And you both talked about physical awareness guiding topology choices. Can you share more specific examples?
Yeah, so as I mentioned, you have two types of NoC structures. You've got your distributed NoC, and then you've got your centralized NoC. And depending on what traffic behavior you have, and also your floor plan information, you end up choosing either one of the two, right? So yeah, you run your modeling, you work at what's best which approach is best, and which structure best suits your floor plan, and yeah, that helps you decide and converge on the right topology choice.
Yeah, just to support that, as well as Piyush, was talking about, from the mesh point of view, for replicated processing elements, or very common uniform processing elements in the mesh configuration, we do actually provide a tiling feature in FlexNoC to actually save a lot of effort in laying these processing elements out.
Okay, another question. How often does a design team need to iterate on the NoC after early system level modeling?
Yeah, so as part of the process, you want to start generating RTL early as soon as you have some specification information. You won't have the optimal topology yet, but you will have at least all your interfaces in place. And by generating RTL early, your design teams can then run their integration flows with the interfaces as already specified. As the design matures, the topology of the NoC will change, but hopefully that doesn't have as much of an impact on the interfaces. So your top level entity is more or less static, and you will have several iterations, several drops of the NoC to deliver to your various teams, whether that's your ASIC integration team or your FPGA team, your Verif team, and your architects as well. So it's several iterations that need to be run as the project progresses until design freeze.
Okay, another question. So you need to integrate System C model for other IPs with the generated System C model by FlexNoC to simulate the traffic?
Not necessarily. If you have traffic traces, instead, it is recommended to run those traces because that is much faster than having the System C representation of your IP integrated in the platform, because it does affect your simulation times. Having said that, it is still possible to integrate the System C of your IPs within Platform Architect, and we've done that before. But it does affect your runtimes, and the whole point of performance simulations is you want a fast turnaround, you want your results back quickly. In order to make your topology changes or your configuration settings, you want to make those changes faster. So you need that immediate feedback. But yeah, it is possible to integrate System C of your IPs within the full system simulation.
Okay, we're coming close to the hour, so last question. How do heterogeneous computer elements such as CPUs, GPUs, NPUs, AI accelerators influence NoC architectural decisions?
Yeah, we see with all of these different compute elements, you have different traffic behavior, different types of traffic patterns that they generate. And the interconnect performs the function of merging traffic from various sources onto few links, which go to your memory controllers, your off-chip memories. So at the point where the merging happens, you could have QoS issues, whereby some traffic is starved of the memory. So you need to perform some kind of QoS settings to ensure that there is fairness amongst all your initiators and they have access to the targets that they're trying to access. So it's more of a QoS fine-tuning step, this.
Yeah, absolutely.
Great.
I'd just like to add very quickly to that as well. The huge throughput we see of data, data traffic going out to memories. We actually also provide what we call broadcast stations as well, to actually, really transmit that data across as many channels, as we can into external memories. So as another consideration for AI SoCs, that works absolutely fine with the QoS system that Piyush previously mentioned.
Great. Thank you, guys. Excellent conversation. This concludes our webinar. Thank you all for participating in the SemiWiki webinar series, and have a great day.
Thank you.
Thank you.